Hi, today's example is going to demonstrate Kubetorch's fault tolerance by resizing the world size of my training while it's running and showing you that it can continue without a snag. It's fairly common for long-running distributed at-scale trainings to run into the issue where at some point in the middle of the training, you actually want to rescale that training. Maybe you want to increase the number of nodes available to the training so that it goes ahead and trains faster when everyone's asleep, or when everyone wakes up in the morning and they need to allocate more compute to interactive research, that you want to scale down that training. However, this process can be really brittle, and if you evict a node from the training, it typically requires restarting from the last checkpoint, babysitting the job, and restarting it manually. In this case, I have 4 ranks up, and the training is going. Here, I'm going to go ahead and grab my other terminal, and in that terminal, I'm going to go ahead and rescale my replicas to 2. This will trigger a termination error here, where the pods are terminated, and that pod terminated signal propagates through Kubetorch as a pod terminated error, which triggers the fault tolerance activities that are to come. Afterwards, you can see that we go ahead and we find that there are 2 workers now, and we restart the process group, and we will resume training shortly. You can see that within about 15 seconds alone, my workers have restarted their training with just 2 ranks instead of 4. I'm going to go ahead and resize this again. If I go ahead and resize this back up to 4, it will take slightly longer than resumption when I scale down because I need to bring up new workers, but the same magic exists. I'm actually going to hold and cache all of my resources, and rather than the slow process of bringing up these extra workers, once those extra workers become alive, I'm going to be able to broadcast my waits directly from the live workers and catch them up extremely quickly and resume training again in about 15 seconds after the workers come up. The magic of the system comes, and you can see that the world size has changed, and now we're going to restart the training with 4 workers. We broadcast the waits, and then training resumes again extremely quickly after that. We could scale this up and down over and over again, but fundamentally the fault tolerance properties of Kubetorch means that almost everything is cached in place as failures hit, and you can restart that training with no flaws. Jumping over to the code, you'll actually see that this fault tolerance is actually extremely easy to implement, and there's no magic here. So what I have here is a basic entry point to my training. I take in some workers count, and then I define my compute with Kubetorch. I say I need some number of workers with 1 GPU each, a given image, and I want PyTorch distribution wired up for those workers. Now that I have this compute object, I can go ahead and take my BERT trainer class and dispatch it to my compute with some initializing arguments. This BERT trainer class is nothing special. It's just a standard regular Python class. So then all I have to do is call this class from my local environment, local being your jumpbox KT run to run it in a pod, or actually your local machine. We define a cache worker, which we're going to use to make a multi-threaded call into that remote training to save the checkpoint every some amount of time. This doesn't block or interfere with the training itself, and we're just doing it purely to the local pod file system. Then we just run the training in a loop as usual. We call trainer.train, and after we complete an epoch, we go forward 1, and this is a very normal training with the caching happening multi-threaded in the background. However, when we hit these errors such as KT membership changed or pod terminated error that we saw earlier, worker membership change happened when we increased the number of replicas, pod terminated happened when we lost some replicas. What we do is we go ahead and reconstitute the process group. So we call .distribute again by taking a new worker count, and this sets up the world size to be the new world size, and then we recreate the process group here, and now we can just continue, and it will continue training as if nothing had happened. So as you can see, catching the errors within the driver program itself is extremely easy. You're just calling the trainer as usual, catching exceptions as usual, and the magic happens when Kubetorch keeps everything in place in the face of a fault instead of falling over or having cascading failures. We make sure that the model checkpoints, the models, and the resources on the Kubernetes cluster stay warm for you for a fast restart. Within the trainer class itself, the only thing that you have to implement is a basic restart logic. When we have decreased the world size, we want to just make sure that everybody is on the same page before restarting. And when we increase the world size, we need to make sure that the replicas that didn't previously have the model have a fast broadcast from the ranks that do. So all we do here is check every replica for whether or not they have a local checkpoint. If they have a local checkpoint, they check in with each other and see who has the maximum epoch. For all the people who have the maximum epoch, we just take the lowest rank, and then we take that lowest rank and we broadcast it to all of the other ones. This is an extremely fast operation. It's traveling GPU to GPU, and it basically takes less than a second to do for the sync process. So you can see here, all I need to do to implement fault tolerance in my long-running training is to just define some basic behavior in my trainer class about what to do after restart and to make sure all the weights get to the right place, and then just have a simple try except within my driver program, which calls my remote trainer service replicas, and that's it. Your training is now resilient, and your VP of engineering can randomly allocate more or less resources to any training job and have it confidently run on.